It's my pleasure here to be with Qiao. So Qiao is a second-year PhD student at the Computer Science Department at Rice University. So he was a kernel developer in VMware before he joined Rice. He is currently focusing on the security implications of P4 programmable switches, such as building security systems using P4 and discovering attack vectors in P4 systems. So it's great to have you here, Qiao, and yeah, take it away. So today you'll be telling us about programmable network security for bring your own device networks. So go ahead.
Okay, nice to meet you guys. I'm Qiao. Today I'm gonna talk about how we leverage P4 programmable switch to build a security system for BYOD scenario. First, let's talk about more about BYOD. BYOD means bring your own device to work. Employees can bring their own devices such as smartphones or laptops to work, and they don't have to use the ones from the enterprise. And this is getting very popular, and the market is large. The result is that employees are happy because they can use their favorite devices, and employers, they save a lot of money. That's why it's getting popular. And the problem is that bring your own device can become bring your own risks. People bring their own devices to workplace, they access emails, they process documentations, and they access sensitive data. However, BYOD devices, they are generally less well managed than their enterprise counterparts. This means that they can be easily compromised. For instance, we might find a lot of Android malware in the applications, or if you have a device and you forget to update your security library, you might be vulnerable. This means that every single BYOD device is more likely to be a malicious one. When they request sensitive data, we have to answer this question whether we should allow or block this request, right? So people have developed a variety of BYOD policies to enforce this access control, such as block access if your library is outdated, or block access if the administrator is offline, for instance, it's not a working time, so we block access. And block access if the recorder is on because you might be recording some sensitive data, for instance, and some other policy might rely on the GPS location. And we call this class of policies context-aware policies because they rely on dynamic context, and they have been shown to be effective in the BYOD security scenario. The challenge, however, is how to enforce these policies. The state-of-the-art solution for enforcing BYOD policy is leveraging software-defined networking. In this paradigm, we install a client module on the client device to obtain the client context, such as GPS locations. Then we rely on the SDN infrastructure to enforce that. When a device issues a request, it starts a new flow. When the new flow arrives at the data plane asks the control plane how to process this flow. This is basically how SDN works. In the control plane, we install a SDN application, and the application maintains per flow information and get the context information from the client module. It makes a decision based on the context. Then it tells the data plane what to do. The data plane will be able to drop or forward the packet to enforce the policy. In this paradigm, the performance bottleneck is the SDN control plane because this is basically a software. It is not a hardware-assisted system, so that if the clients are malicious, they can launch DDoS attacks against the control plane by sending, numerous context updates. This is also sometimes called SDN saturation attacks. So in this work, we investigate how we can address this scalability problem in this paradigm. And we have found that that the new opportunity is P4 programmable data plans, which is quite different from traditional SDN hardware because it has many new hardware features, such as a programmable parser. It can support customized protocols, and it can perform arithmetic computations, and it supports stateful processing. And the speed of the P4 programmable data plan is fast because it's basically hardware and not a general purpose CPU. It can process very high throughput traffic within one microsecond delay. And most importantly, we can reconfigure the hardware using P4 language, which is a high level language. So we ask this question, how we can leverage P4 switch to address the limitation of the SDN-based solution we just talked about. To answer this question, we designed a system called Poise. Poise has defined a language for network operators to express BYOD policies. Then the P4 compiler takes the policy and generates device configurations, telling the device side how to collect context, which context to collect, for instance. It also generates, most importantly, a P4 program, which will be installed on the switch. Then we will also show how we design the P4 data plan to enforce the policy in a dynamic and efficient manner. For the rest of the talk, I will be focusing on the design of Poise. We start with the Poise language. Poise language is used for writing context-aware policies in a simple way. Let's take an example and see how it works. For instance, I want to write a policy and say if the SSL version is small, then we should block the access. It's going to be simple to write such a policy. First, we define a predicate. Then we define what we should do if the predicate is satisfied. In this case, we should drop. Then we just combine them together using if, else, then. That's it. Then we show how we compile, how we convert this policy to a piece of P4 language. First, we identify the context field, in this case, the SSL version, and we generate a P4 header definition. In this case, it's a 16-bit long customized header. Then we identify the security actions, which is the if else, if then else, and then generate a table. Basically, the table looks at the key, which is the version number, and it performs a match. If it is smaller than the threshold, then we drop. We make a decision, which is drop. Otherwise, we make a decision, which is allow. So we have seen how we generate a piece of P4 program so that we can identify the customized header, and then we make a security decision. Next, let's put it together and take a look at how the system runs at runtime, which is how the data plan works. The data plan design is non-trivial, so let's start with a very simple paradigm. We tag every single packet. For each packet, we embed the SSL version, the context in the packet. And then when the packet arrives at the P4 switch, remember that we have a table which can match against the context field. It makes a decision based on the context, whether to allow or drop. Then it removes the context because it's extra. We have to restore the packet. Then based on the decision, it forward the traffic or it drop the packet. This looks very simple, right? We just add another field and makes a decision based on the field. However, there is a big problem in this design because it has very much traffic overhead. For instance, if we have 20 contacts and each context takes 4 bytes, the result will be we have to send 16% extra traffic. This is unacceptable, a lot of overhead. So this suggests that we should probably not tag every single packet because of the overhead. Our solution is send context using dedicated context packet occasionally instead of tagging every packet. Occasionally also means that we can do that periodically. For instance, we send one context packet which carries the context every 1 second or every half second. And then we can keep the data packets unmodified. So based on this idea, we design a novel in-network primitive to realize this idea. This runtime primitive has 3 properties. The first is dynamic. We periodically send a context packet from the client side. And when the context packet arrives at the P4 switch, the P4 switch remembers the decision based on this context packet. Then, when the next packet arrives, it enforces the latest decision made from the previous context packet. So we are making dynamic decisions based on latest context. So the decision could be allowed or it could be dropped. Another property is that we can adjust the accuracy and also the overhead by tuning the context packet period. For instance, we can make it coarse-grained, which means we can send the context packet every second, for instance. Or if you want to make it more secure, you can send context packet more frequently, but it will cost more overhead. But again, the key point is that we can adjust, we can tune this accuracy versus overhead trade-off. Another property is that efficiency, because we only send the context packet periodically, we don't have to tag every single packet, so the overall traffic overhead is small. Next, I will be talking about some more details on the P4 switch. The key point here is that the P4 switch has to remember the decision for the following data packets. And we realize this using a flow table. It keeps per flow information. For instance, the flow table might look like this. It has the flow ID as the key and the latest decision as the value. When a context packet comes in, it might, add a new entry because this may come from a new flow. In this case, we add a new entry. If the context packet is from an existing flow, we can update the entry. In this case, we change the decision to drop. For data packets, it's easier because we just look up the table and find the corresponding decision and enforce the packet. In this case, this flow we should allow, and for the other flow we should drop. This is the key data structure we have used in the data plan. But there is also a challenge because installing new flow in the P4 switch can take some time. It is not trivial. Basically, when a new flow comes in, we should send a request to the control plane and ask the control plane to do the installation. And then the control plane, it install the entry. However, the delay is non-trivial because it can take several milliseconds, several microseconds. It depends. But anyway, the point is that when the context packet issue the insertion request, maybe after several packets, the entry can get inserted. So we don't know how to process the packet in between because we don't have any entry in the table. By default, we should drop them, but if the flow is benign, we shouldn't do that. So basically, we don't know how to process that. The solution we have used is in adding another extra data structure called cache, and we buffer these updates in the cache. The cache, different from the match action table, it is not implemented as a match action table, it is implemented as a register array. So it's completely in the data plan using data plan onboard memory. So the property of the cache is that any changes in the cache is in real time. So we don't have to worry about the delay because of the control plane interaction. Again, when the context packet arrives, we ask the control plane to insert the entry, but also at the same time, we buffer the entry that should be inserted at the cache, so that when the following data packets arrives, it misses the table, but that's not a problem. We can look up the cache and get the result. Then we know how to process that. So that in this short window, we have the cache as the backup. We don't have to worry if the match action table is empty. After maybe 1 millisecond, the table is populated and other following packets won't have to go to the cache. It can directly go through the table and enforce the decision. Introducing this cache is also non-trivial. It has many problems such as how to handle cache clearance and how to handle DOS attacks against these data structures, but we can't cover all the details. I refer you to read the paper if you are interested. So this wraps up the design. We are going to talk about how we evaluate Poise and the results. We have implemented a Poise prototype. The compiler is based on Bison Flex, and we also implemented the Android client module. It is basically a kernel module in Linux. And we evaluated Poise, the system, using a real hardware Tofino switch. We have evaluated many properties, but in this talk, we're going to talk about the most interesting one, which is why Poise is resilient to the control plane DOS attacks we have mentioned. So we take the SDN-based solution, which is the PBS. It enforces BYOD decisions using SDN infrastructure. And the methodology is that we assume, we simulate a DOS attacker, which sends a lot of context changes to the network, and we measure how normal user traffic are affected, or whether or not they are not affected at all. We'll measure that. The first experiment we did is that we measure how the per packet processing delay under different attack strength. As we can see, when the attack strength is high, the SDN control plane is overwhelmed and it takes more than a second to process every single packet. This is because the control plane is busy processing all the context updates. Context updates go to the control plane, and which is software, and the software, always has performance problems. But Poise, it remains constant. This is because Poise is in process all the context changes completely in the hardware, and the performance is guaranteed because it's a pipeline hardware, which is totally different with general purpose software. The second experiment is similar. We measure on the different attack strings how many new flows we can install. Again, the SDN solution failed to install new flows because the control plane is busy, but Poise can always do that because the control plane is not processing any context changes. It's all the context changes, again, are processed in the data plane. So the takeaway is that Poise is resilient to DOS attacks to the control plane because of its hardware pipeline nature of the P4 switch. Finally, we're going to conclude our talk. We are motivated by the question how we can provide better security, network security with P4 switch. And we talk about a particular case where we use P4 to enforce BYOD policies. And we design and implemented Poise, which leverages P4 for enforcing policies. The key takeaway by doing Poise is that we can transform the hardware features like the pipeline, the performance thing to security benefits. In this case, we are resilient to DOS attacks. And that's all for the talk. Thank you. And I would like to take questions.
Hey, thanks, Qiao. That was that's really cool. Very interesting work. I guess I have a few questions, kind of starting off from kind of smaller details, just trying to like clarify my own understanding, and then we can discuss where you want to take this project further. So let me start. So I guess one. So can you explain a little bit more about how the context packets are generated, and are so first of all, are these context packets per TCP connection, or is it like a per device entity, or is it per application entity? Like at what scope should we think about these context packets?
So the question is that how we generate context packet, is this correct?
Yeah, so like at what scope do you kind of generate? So let's say I bring up a new, I install a new application on my laptop. Do you think about, if that new application has to connect to the enterprise network, would you have to like generate a new context packet for that application?
Okay.
So I mean, and also like, do you make any modifications to like TCP connections that these applications?
I see.
So things like that. Yeah.
I see your point. So I want to clarify that the context packet is on a per flow basis, which means that for each flow, we generate context packet. It basically means that whenever you open a new socket, we hijack your new socket and send out a context packet immediately. Which means that even before you send any data packets, we already send one context packet. This is for the P4 switch to establish the connection, yeah, and that's the first context packet when you open the socket, and then we send the context packet per flow periodically for every established flow. And when the flow ends, we send a final context packet, and then that's it. Yeah, so it's based on the opening and the closure of the flow.
Nice. Okay. So you would so the way to think about these context packets is they are kind of interspersing all of the data packets in the actual TCP stream. So would they look like they are a part of the connection then to the P4 switch? Is that how you imagine them to be, or should I think about them as totally asynchronous? Like you send a packet, as soon as the connection starts, and then you also send a packet kind of periodically, but the TCP connection itself is sort of unchanged.
The TCP connection is not affected because the context
is unchanged.
Yeah. This is because when the context packet arrives, the P4 switch, the P4 switch drops the context packet, so it won't arrive to the other side. So it's completely transparent to the transport layer.
Oh, okay, awesome. That's helpful. Thanks. So does that also mean that they are kind of? So I mean, I guess you need to kind of worry about the timing of these things as well, right? Like, so if there is some sort of reordering and jitter in the order of packets between the TCP connection and the context packets, I mean, is that a concern at all? Like if, so let's say, you had context 1 that has to apply to TCP packets, 1 through 5, and then context 2 that needs to apply to like 6 through 10. You could have a reordering which, makes the context appear later or earlier. I mean, is that a concern, do you think? Maybe not.
I do agree that reordering if the reordering happens a lot, it might be a problem. For instance, not only jitter reordering, also packet loss, right? We might lose context.
Lose the context. Right.
Yeah. But in our work, we didn't think that is a big concern. The reason is because the P4 switch, as you can see, it is connected to the AP. Then it connects to the device. This link is very short, right? It is even before the packet goes to the core network. So this is basically the first hop of the device. So we assume that the network condition here is good. So we don't consider.
No, that's that's very reasonable. Yeah, I think this could be like a nice solution in the context of like an edge device. It could run as part of the if you have like a P4 programmable access point, you could run it right there, or you could certainly run it as the first hop beyond the access point, which I think would be pretty useful. Okay, that sounds really good. So were there any features in P4 that you wish you had, or like any, switch hardware features that you wish, gee, if I had that, that would, my life would have been so much easier?
You mean P4 switch, what features they don't have but I want?
Exactly. Yeah.
Okay. The biggest feature we want is perform crypto in the data plane. I don't know how hard it is, right? Because currently the P4 switch can only do simple calculations on the data plane. But if you wanna decrypt or encrypt the packet for crypto protocols, you have to go to the control plane again. This is actually a concern. It could be a concern. For instance, in this case, in this work we do not encrypt the context because on data plane we cannot perform decryption. And we had a lot of discussion regarding this point, and that's one of the reasons the reviewers wanted to reject the paper. But right, if we had this feature, it could make everything much easier. Yeah.
I see. So I guess the problem is sort of the privacy concern of sending out this context in plain text, I'm assuming.
And also integrity, authentication. So this kind of problem. Right. Not only Poise, some distributed switch systems, they have peer-to-peer communication between two switches. And this is not guaranteed, the integrity and the privacy. Basically, everything is in plain text.
Right. Yeah, talking about integrity, I mean, how do you guarantee that the host, like the endpoint context that's being sent out is actually valid, right? I mean, like you have an Android app or, a module that's actually running on the local system, but the local system could have been, taken over by a malicious actor, right? So like, how do you, I could pretend, on my phone, hacked phone, I could pretend that I have a higher SSL version than I do, for example, or I could pretend to be someone that I'm not. So like, how do you deal with that? I'm assuming it's a big problem for any kind of context-aware policy enforcement.
Right. That's a good point. In our work, again, our trust module is that we trust the on the client side we trust the OS and Android platform, and we also trust our the software we inserted the hijacking thing. So basically, we assume that the applications cannot arbitrarily send raw packets. They don't have access to the raw sockets, so they can't use like sudo send a packet and craft the packet and send it to the network. And we also trust that the link here and at access point and the link here is trusted. So our trust module excludes this problem. But again, if we can have a better trust module, if we have better features supported in the P4 switch, yeah.
Cool. This is really cool. So I guess kind of more broadly, like I was thinking, I mean, given that you're able to enforce these sorts of context-aware policies using these high-speed switches, do you think some of your technology could be reused to implement like a more general intrusion detection system like BRO or SNORT within the context of a P4 switch? I mean, do you think that's actually possible? So, I mean, so BRO or SNORT, I mean, the rules, presumably, all the stateful components of it, they are kind of very similar to the state, the flow level state that you have to maintain in Poise. And presumably the kind of, I mean, so the rules themselves would dictate how the state actually evolves. But of course, you would need to have some component of, some deeper packet inspection than what you might normally have on a switch. So I mean, any thoughts on that? Like, what would it take to kind of take the technology that you have and sort of really implement one of these intrusion detection kind of systems, or is it sort of too far out to even think about that?
So your question is how we can enhance the the needs, right?
Yeah, so how you can enhance the current Poise, like the system that you guys have developed, do you think you can actually build out like a network intrusion detection system using this?
That's a good point.
Mm.
So actually, a recent work from our group is kind of similar with what you have been talking about, because if I understand correctly, the network in intrusion detection system, they use customized hardware. Is this correct? Which means that they cannot easily reconfigure the hardware, right? But they can process traffic at a very high speed, and they can do a lot, such as DPI, right? And the P4 switch, it has a kind of an opposite feature, which means that they are easily reconfigurable, but they cannot support complex algorithms like DPI. Maybe in the future they can. So it seems that they can work together and do more. For instance, if you deploy a P4 switch together with traditional middle boxes like intrusion detection systems, and because P4 switch can do routing also, right? So you can do routing and security at the same time. You know what I mean? I mean, if you think that this flow needs DPI, then you pick up a path for this flow, and it goes to path A, which has the middle box A and B. Otherwise, you go to middle box C. So which means that you can balance the workload based on your observation in the P4 switch, so that P4 switch can something, you can design a hybrid system for them to work together for better load balancing. You can also offload some functionalities from the middle boxes to the P4 switch and to save cost, right? Because presumably the middle boxes, they are maybe more expensive, and it's harder to upgrade. But P4 switch, you just write a program and reinstall that, right? Yeah, that's a line of work we are been thinking about.
Cool. It also looks to me like in your wish list of features that you wish you had on a switch, it seems like deep packet inspection might be among them as well. Because if you could do DPI, then I think you have the entire. It looks to me like you might have like the entire set of tools you actually need. Kind of just implement a fully featured network intrusion detection system on a P4 box. So it seems kind of interesting that. I guess there's nothing sort of fundamentally preventing you from defining a parse graph that allows you to like extract all the deeper information. But I guess there are certainly resource constraints on a P4 switch, like the number of packet header vectors, or so like specific resources that are sort of really heavily used when you have to like go deep into the packet. So yeah, that could be kind of an interesting line of inquiry on its own. But I think I agree with you. Like in the short term, it seems like a good sort of hybrid design might be like a good balance between having like a potentially expensive kind of a middle box solution, but and something that can actually process packets really fast, which is also like reprogrammable. Cool. The other interesting aspect that it seems like your design is actually looking at like a single switch at this point. Have you considered kind of network-wide sort of policies? For example, like I can imagine that there might be context that you need on the return path from the, in the picture that you've shown, like, the packets from the enterprise server back to the device. You don't actually have, if you change the servers inside your enterprise, maybe those could also carry the context, but otherwise it seems like you have to have some way of, if you have to have like a ContextAware policy on the return, the packets, then like you need to have like some way of both the packets in the same place. You see what I'm saying? Like, so there has to be like some element of network-wide visibility here that, kind of ensures that, you see the traffic going both in the forward path and the reverse path, right? Is that something that came up at all?
Right. Basically, we are focusing on a single node, right? And we agree that a distributed setting is more realistic. But fundamentally, that's we are currently we have been thinking about a particular challenge in a distributed setting. For instance, you might have 3 P4 switch at ABC, right? And P4 switch A wants to make a decision, but it happens. The case is that the decision A wants to make depends on B, and B has a new decision depends on C, right? So which means that they have to make a collaborative decision, and they might want to share some state. In other words,
what's an example of something like that?
Let me give you an example where switch A wants to make a decision whether this request should be allowed. And the policy says, basically the policy says everything, right? The policy says that if switch B is already, if another user is already reading the data, is already reading the sensitive data, but the path is going through B, and another user going through A cannot read the sensitive data at the same time. So it's so yeah, basically we want to make sure that a single user is accessing the data, but not two users at the same time. So this means that these two switches have to work together, and they have to exchange information. They have to maintain consistency. This means that they have to have some kind of a peer-to-peer communication to exchange their state. And we found that there isn't a lot of work for P4 switch to maintain shared states, to maintain consistency between each other. So another thought from our group is, maybe to design a new protocol to do that. And before that, we don't think we can easily implement a distributed Poise. So there is basically a long way to go,
Right. Yeah, it certainly seems like you would run into all the problems of kind of distributed consensus, right? Like you would have to like agree on the state, and the sort of the agreement has to be, especially when it comes to security policies. For example, hey, this piece of secret state cannot be accessed by more than k parties at a time. Like all the nodes that grant access to that state now have to agree on how many current users there exist to that piece of state, right? So I think like you probably would it's kind of interesting, you would run into kind of all those sorts of issues. Interesting. I guess people have tried to implement forms of consensus over P4 switches and P4 networks. So that could be, you could certainly leverage those existing works and all of the stuff in the distributed systems literature to try and make that happen. Cool. Very cool. Awesome. So I guess like the last question I have is maybe more of a clarification than a question. So if you go back to one of your evaluation results, if you go down, I guess, to the part where you talk about the saturation attacks. So yeah, so one thing that was a little fuzzy to me was when a new context packet arrives at a switch, it would end up sending that context packet to the control. The switch would end up sending the packet to the control plane, right? Like, so I understand that existing packets in the data plane, like data packets, would not have to go through the control plane. So that I understand. So that's already a benefit of having, like a data plane focused design, like with a cache that you've developed. But if you just send more control, these sort of context packets, I mean, don't you end up seeing all of those context packets also in the control plane?
So there is for each flow, only one context packet will end up going to the control plane, which is the first context packet, because we don't have that entry. Remember that we have to install a new entry for, basically for the first context packet. But for all the following context packet, we don't have to send them to the control plane. This is because we can installing a new entry goes to the control plane, But updating the decision here, we have some technical, we have some technique to do it completely on data plan. So yeah, the way we do that is basically we maintain an index here, and the index points to the array somewhere else. So we don't have to change the table entry, but instead we only change the register it points to. So to update the decision, we don't have to go to the control plan.
I see.
Yeah,
I see. So if I understand what you're saying, the first context packet of a flow is something that would require the control plane to actually actively interfere and actually install a new entry. But like for all subsequent context updates of the same connection, you can pretty much do it on the data plane. That's I see.
Exactly.
Okay, that's neat. That's neat.
Yeah.
So I guess if I had to DDoS your system, I would have to open a lot of new flows. Like that would be the way to saturate the control plane.
Yeah, that's something that we have to consider. Right. But here we are focusing on mostly for existing flows. We can process the context on the data plane, but for new flow, that's a different story, right?
I understand. Cool. That's really neat. I didn't appreciate that like existing flows kind of get processed directly in the data plane. Okay, so that's all I had actually. This is really cool work, and I'd be excited to see what directions you all end up taking it in. So maybe you could, if you want to share any other thoughts with the community, maybe you could do that. I'll let you have the last word.
You wanted me to have the last word?
Yep.
Right. I thank you again for your hosting this meeting, and especially in this difficult time. And right. And yeah, pretty much appreciate your coordination, and also thanks, Michelle. And yeah, I would like to but I think we have some more thoughts on about research, but we can take it offline. Yeah, basically our group is thinking more about P4 programmable smart NICs and so on and so forth. But yeah, so we can take it offline.
For sure. Yeah.
Yeah.
Awesome. Thanks, Qiao.